Welcome students. Today our topic is grading of underground cables. Now grading is defined as a method of equalizing the electrostatic stress in the dielectric of the cable. Grading makes the cable of the same size to function at operational voltage and also at higher voltages. Grading of underground cable is necessary for uniform electrostatic stress distribution in cable. If the stress distribution is uneven, then there is a high chances of breakdown in outer insulation layer. One may think that if the thickness of the insulation layer is increased, then it may prevent breakdown, yes, but doing so will increase the cable size, which is undesirable. So the most suitable way to keep the uniform stress distribution in underground cable is grading, and this grading is achieved by the two methods, that is capacitance grading method and inter-sheath grading methods. Now before going to these methods, we are just looking at dielectric stress in a single core cable. Now the maximum the maximum electric field of the electrostatic stress that an insulation material can withstand without losing its insulation, or we can say without losing its insulating properties, is described as the dielectric stress. It may also be defined as the voltage or the maximum voltage required to produce a dielectric breakdown through the material. It is expressed in terms of volt per unit thickness. It is also a measure of potential gradient at a specific point. Now you look general pictorial view of a or cross section of a single core cable, which D denotes the capital D denotes the internal sheath of or we can say diameter. Small d is the core diameter and G is the potential gradient of the cable. Now from this figure, the potential gradient G at a point x meter from the center of the cable can be calculated by using G is equal to Vx. No, from this we know that so G is equal to Q by 2 pi epsilon 0 epsilon r x volts per meter. Now where Ex is the electric intensity and by definition G is equal to Vx. The potential difference V between conductor and sheath is calculated using the equation V is equal to Q by 2 pi epsilon 0 epsilon r log E d by d volts. So from this we calculate the value of Q which is 2 pi epsilon 0 epsilon r V by log E d by d. So by this we calculate the value of Q. Now by substituting the value of Q, potential gradient G is obtained as shown in figure. It also states that the potential gradient G is inversely proportional to the distance x. So we put the value, then G is equal to 2 pi epsilon 0 epsilon r V upon log d by d into 1 by 2 pi epsilon 0 epsilon r into 1 by x. So finally we got the value of G. Now G max, which is equal to 2V by d log E d by d volts, and G minimum is equal to 2V log d E d by d volts. Now the ratio of G max and G minimum is we get by this formula, which is equal to the ratio of the diameters. So the surface of the conductor experiences a maximum variation of stress and reduces considerably for the layer away from the conductor. It is an important factor when designing a cable. So the grading of cable have to be done. So the grading of underground cable is categorized into two categories, that is capacitance grading and inter-sheath grading. Now for the capacitance grading is achieved by using composite dielectric, that is various layer of insulation or various layer of different dielectric are arranged to ensure that the potential gradient remain constant. It is inversely proportional to its distance from the center. A uniform dielectric stress is maintained in the cable, generally 2 or 3 dielectric having different relative permittivity, which have the dielectric with highest permittivity is placed near the core of the cable, and subsequently the other dielectric layer are arranged in the decreasing order of permittivity. So here we have the cross section of the three lobe cable. In this figure, the three dielectric layer have been considered, whose inner radius is R1, R2 and R3, R1, R2 and R3, and the outer layer resistance is R, and the diameters are D, D1, D2 and D3. The relative permittivity are also epsilon 1, epsilon 2 and epsilon 3 respectively. From this, if the three dielectric layers are subjected to maximum stress, then the potential difference of the layers are 1 upon epsilon 1 d, which is equal to 1 upon epsilon 2 d1, which is 1 upon epsilon 3 d2. So epsilon 1 d is equal to epsilon 2 d1 is equal to epsilon 3 d2. For the potential difference across the inner layer, we have we just integrated the g, v1 is equal to, which is equal to d by 2 to d1 by 2 gx, and we got the value of v1. Now similarly, the potential difference across the two layer v2 and v3 are, we got the value of v2 similarly and v3. Now the total potential difference between core and the outer sheath is, which is equal to v is equal to v1 plus v2 plus v3. We add 3 voltage and we got the value of the total potential difference between the core and the outer sheath. Now when we talk about the inner sheath grading, it make up the homogeneous dielectric. It is divided into different layer by inserting metallic intersheaths between the core and outer sheath. This provides a channel for charging current. The metallic inner sheath are maintained at adequate voltage level as they are connected to auxiliary transformer. This ensure uniform potential gradient throughout the dielectric of the cable. Now we have this figure also. In this figure, the three layer of insulation are separated by two intersheath at definite voltages V1, V2, and the core of or conductor voltage is at V. As each intersheath layer experiences different potential level, it can be treated as a homogeneous single core cable. Now from this, G1 is equal to V1 by d by 2 log d1 by d, and we have the G2 and G3 maximum. We have the value for the homogeneous equation, or for the homogeneous dielectric, we have G1 maximum is equal to G2 maximum is equal to G3 maximum. So we put all three equal, so which is equal to G max. And also we can say that since all these potential differences are in phase, since the cable is in fact a series of capacitor in series, we also have, we can say that V is equal to V1 plus V2 plus V3. We also can say that. Now the advantages of the underground cables are due to the grading, due to reduced dielectric thickness, the cable size is smaller. So due to this, the cable size is smaller. So up to the very high voltage we can use the underground cables. Chances of dielectric failure is reduced in capacitance grading. So it is very big advantage, and the dielectric loss is less at lower voltages. Now it certainly have some drawbacks, and that is in inner sheath grading method, installing the sheath potential is difficult. Intersheath are prone to damage during transformation or installation, and the dielectric loss is more for higher voltages. These are the drawbacks of the grading. Now we are just see that the selection of underground, how can we select the underground cables. So we have certain points, by this we can select our underground cable. The first one is voltage of cable, up to the what voltage level we are using. So as per that we are selecting our underground cable, the current carrying capacity of the underground cable. So we have to identify the how much current that our cable can carry, or how up to a high voltage or what voltage it will be sustained. So we have to also select the cable on the current carrying capacity. Next is the short circuit values. What are the short circuit values of that particular cable? So on this point we can also consider now the type of conductor, which type of conductor we are using. We have a 3-core single core cable or 3-core cable, also we can consider that, and it also have a 4-core cable, or it has a neutral or not, and it also includes the which type of insulation we are using, on which level of insulation we are using. So on this point also we can select our cable, and what are the method of insulation or installation we are using, and the shielded cable or unshielded cable is also considered, because if shielded cable is there or unshielded cable is there, we have to consider. And the most important is economics, what is the price of the cable. So on that point of view we are also selecting that cable, and the environmental condition, on which environmental condition we are using, it is a very dry place or it is very humid place or very rainfall is occur, so it also depend, and for which particular application which we are using that cable. So it on these points we are selecting our underground cables. Now that's all for today. The next topic on this power system we are discussing in next class.